The first thing we want to do is generate an energy spectrum of the entire remnant. We have seen this before. We open DS9, go to Analysis, go to Virtual Observatory, connect to the Rutgers primary MOOC, select ACES observation of CAS A, OBS ID 114, and there it is. For clarity, so we can see things a little better, let's just change the scale to a logarithm. And now we'll click on the central object. When we click on the central object, we create a region. We can click again to select the region, and now we're going to drag it out so that it encompasses approximately the entire remnant. Now we can go to Analysis. Let's cut off our analysis program here, and then cut off our Chandra Ed analysis tools. And we're going to look at the quick energy spectrum. And here we have a plot of what the energy output of CAS A is like. Each one of these peaks represents the presence of a different chemical element. Now, if you do this observation carefully and this analysis carefully, we can look at this particular result, which represents the same thing as we looked at just now, except kind of color codes all of the photons in an interesting fashion. Notice that everything red here is up to about 1.5 keV. Then we get a green region here, color-coded green, which goes up to a little over 2 keV and includes the lines of silicon that we see here. And then a blue higher energy region that includes sulfur, argon, calcium, and iron. So we can do something now very exciting. Let's actually create our own three-color image based on the energies that we see here. We're going to look at the photons less than 1.5 keV in red, 1.5 to 2.2 in green, and 2.2 to 10 keV in blue. This will allow us to isolate the various emissions from neon, magnesium, silicon, sulfur, calcium, etc., etc. So we can return to DS9 and do the following. First, I'm going to ask you, only if you have a Windows machine, this is a bug that Windows has presented us with that we have solved in the following fashion. All I'm going to ask you is to make one small change to your preferences. And if you are doing this on a Mac, you don't have to worry about anything. Go to Edit, Preferences, and where you see General, right down here in Dialog Box, just make sure that the Windows radio button is checked. This will allow you to be able to save your files in the proper fashion. Okay, so now the first thing we're going to do is go to our analysis, Chandra Ed analysis tools, and we're going to create an energy filter. We click on energy filter, and you see that we can enter the values for the two lower and upper energies that you would like to look at the photons for. So here we have 0.1 keV. And over here, we're going to go up to 1.5. We click OK. And now you see next to our original frame, we now have selected out, although you really can't tell that these are photons from 0.1 to 1.5. Okay, these actually are, and it'll be interesting, I'll show you in just a second, an interesting way to show that, in fact, that's all that there is here. Well, the first thing we're going to do, notice that this frame is selected with this little blue line surrounding it. We're going to save this. We want to save this file. And we're going to save it as a FITS file, and we're going to put it on our desktop, and we're going to call it red.fits, because that's going to be our red color. So we save it. Okay. And now, after we do that, we click back to our original. Okay, here we now clicked on our original frame, and now the blue line is surrounding the original frame. And now we're going to do another energy filter. And in this particular case, we're now going to use as our low energy 1.5 keV, and our high value is going to be 2.2. We click OK. And bada-boom, now we've got our green filter energy from 1.5 to 2.2. We're going to save that. And we're going to save it this time instead of red. We're going to call it green. Whoops! Green.fits. We're going to put it on the desktop, and we're going to do a save. Yes, we'll do that. Okay, now I'm going to ask you an interesting question now. What would happen if you didn't click back to the original frame, okay, and you did another energy cut? Why would that happen? Why don't you try it? In other words, here's our 0.1 to 1.5 frame. What would you get if you did an energy filter on this frame from, say, 1.5 to 2.2? You'll get an interesting thing, and you'll learn a lot about what we're up to in this particular situation. Anyway, we're going to now click back to our original, okay? And we're going to do our last energy filter. And that energy filter is now going to be 2.2 keV up to 10 keV. We're going to click on that. Here it is. We're going to save it. And this one we're going to call, guess what? Blue.fits. We save it. And now, watch. We're going to combine them all. What I want you to do now, or what we're going to do, is just for clarity, you can see that as we increase the number of frames displayed here, it kind of looks a little grotty. So let's delete all of these frames, and we'll start from scratch. We go to Frame, we go to Delete, 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 boom, all gone. Now we're going to do something really cool. We're going to go to Frame, and we're going to click on New RGB. That's for red, green, blue. So when you do that, up comes this little teeny box, and this is telling us that we're currently working with the red part of our frame. We go to File. We're going to Open, And guess what we're going to open, folks? We're going to open the red.fits file. And there it is in red. Okay, now let's go. What happened to our little... Ah, there it is. Okay. Now let's click on green. We go to File. We open. Guess what? Green.fits. And that's superimposing the green photons over it. They're really not green photons, right? They're 1.5 to 2.2 keV X-rays, very, very high energy. And we do it one more time with blue. So we do blue, and we go to File, Open, and now we look at our blue.fits file, superimpose, and now there it is. Look at this. This is really, really cool. But now we can do more. We can select each of these colors and adjust our color map parameters. This is really, really neat. Okay, let's go to color, and let's just kind of extract out the color map parameters here. And we'll place them over here. And now we can manipulate the contrast and bias in each one of these channels until we get something that we like. So what I'm going to do in this particular situation is first select our red channel, and I'm going to go to scale, and okay, it's in logarithmic form anyway. I'm not quite sure what min-max is doing checked here, but we've got logarithm here, and let's just kind of adjust this a little bit. So I'm just gonna, oh, you know, this is cool to look at. Let's pull this out of our way here so you can see what happens to the color map parameters. Remember, you can utilize the mouse, right click, and you can go left and right and adjust the bias, up and down and adjust the contrast. So we can get something like, oh, let's try somewhere in here. I'm not sure which ones I'm going to like the best. This is not too bad. Okay. Now let's go to green. We can do the same thing with the green channel. Whoops. Well, that's kind of interesting. Now let's go to the blue channel. Just kind of adjust up and down here. And now you have generated a energy plot. Instead of just a function of intensity, we're now looking at specific energies associated with this supernova and looking at the lowest energy ones in the red regime, the middle energies as a green component, and the higher energies as blue. And you can have a lot of fun with this stuff, just generating these kinds of images and see what you can come up with. The best one that I came up with, I'm going to actually enter it into the parameters here. So you see what this one looks like. I'm going to go to red, and I'm going to change the red weight to 3.6. Oh, it was pretty close at 3.6. 3.6, and the bias I wrote down is about 0.715. That's pretty good. And then for green, I seem to like contrast of 0.987. That's pretty close. And bias of 0.51. That's pretty good. And then for blue, I seem to like contrast of 4.95, 4.9, well, that's close enough, and 0.6. And there you see it. Okay? Not sure why I like the green like this, but I could just kind of adjust that if I wanted to a little bit. Kind of de-emphasize green a little bit. There we go. That looks pretty neat. Okay. I almost forgot the most important thing, and that is when you're satisfied with your image that you have created, you can go to File, click on Export, and choose one of these photographic media formats. I usually like PNG because it's lossless. You click on that and save as whatever name you want to give it. Let's call this CAS A5. Click on Save, and now you will have it on your desktop or whatever file folder you chose to put it in. And it'll be a convenient way for you to be able to display this image and any others that you might create. So let's go back to the blackboard and see what we can learn from this in exploring our results that we just generated here further. Here are 3 different representations of what we just did, with various scales and color map parameters selected. What we see immediately is that all of these representations are asymmetric. Whatever is happening here, it is not happening everywhere at once and in the same way. You will be exploring this further in your homework this week. Indeed, this area is also a subject of intense research in the astronomical community. We really do not fully understand the fundamental nature of supernova explosions. How are they triggered? How do they evolve through the interstellar medium? We have certainly made progress in answering these questions, but exciting work remains to be done. The progenitor that led to the development of CAS A is an example of a so-called Type II explosion, a core collapse supernova. A massive star greater than about 8 solar masses suffers a spectacular implosion because at the end of its life, it can no longer generate enough energy to support itself against the ever-vigilant force of gravity. The collapse stops abruptly when neutron degeneracy sets in, and the material then experiences an incredible bounce, literally like running into a brick wall, thereby sending a shockwave back outward through the star, which starts the process of forming the remnant that is still evolving today. Next week, we will meet another form of supernova, the so-called Type 1As, which occur in binary star systems and involve white dwarf stars. The observation of these objects led to a remarkable discovery about 15 years ago, namely that the universe was accelerating despite the pull of gravity between its constituents due to some mysterious form of dark energy. The universe is indeed filled with surprises. So we have come full circle. The ancient star that once shone in the night sky billions of years ago has exploded and sent out the material for the birth of future stars into space, where someday, possibly billions of years from now, the calcium we see in the spectrum may ultimately form into bones, and the oxygen may form part of a planetary atmosphere where life may flourish. So things are not so bleak after all. Even though our sun may die, The seeds for its rebirth are contained within itself to be recycled, possibly endlessly, through the vastness of space and time.